Pop quiz. Which one has electrons that can move easily? Copper, rubber, or both? Lock in your answer. We'll come back to it in a minute. And to answer that, we need to zoom in to the atomic level. In this video, you learn how single atom energy levels turn into energy bands in solids, and why that helps explain conductors versus insulators. Start with one atom. Its electrons live in discrete energy levels, like rungs on a ladder, and Pauli's exclusion principle says two electrons can't be in the exact same state. Now bring two identical atoms very close. Their orbitals start to overlap, meaning the electrons are no longer confined to just one atom. When two atomic orbitals combine, they form molecular orbitals for the two-atom system. One original level splits into two nearby levels, a lower energy bonding level and a higher energy anti-bonding level. This splitting is super convenient. Instead of forcing electrons to pile into one identical level, the system creates two slightly different levels. Now electrons can spread out, and Pauli's rule stays happy. And it's not just the lowest level. The same idea applies to other orbitals too. Each matching pair overlaps and splits into two close-by energies. What if you add a third atom? Then three orbitals overlap, and that one original level turns into three closely spaced levels. In general, if n atoms overlap, you get n very similar energy levels. In a real solid, n is enormous. You're talking about an astronomical number of atoms packed together. So those n levels become so tightly spaced that the gaps are practically invisible. Instead of drawing billions upon billions of lines, we treat them like a near continuous range of energies called an energy band. Different original orbitals create different bands, stacked by energy, and between some bands, there may be a gap, a region of energy that electrons in the solid simply can't have. Each individual level can hold two electrons, so a band formed from an s orbital can hold 2 times n electrons. A p-type band has more room because p orbitals come in more orientations, so its band can hold even more. So what's the real difference? In gases, atoms are far apart, so electrons have discrete levels and must jump between them. In solids, atoms are close together, so levels crowd into bands where many nearby energies are available. Let's use a simple example. If the highest occupied band is partially filled, electrons can shift into nearby empty spots inside the same band with very little fuss. That makes electron motion easy. That's a big reason metals conduct well. When you apply a voltage, plenty of electrons have nearby available energies, so they can flow through the material. Here is a common misconception. It's not just about having electrons. Almost everything has electrons. The key is whether electrons have available nearby states to move into. So far, we've covered how overlapping orbitals split into many levels, and how lots of levels packed together form energy bands in solids. Want to check your progress? Tap the link for a quick practice test and a concise study guide tailored to this lesson. Quiz yourself, skim the highlights, and jump back in. Now let's connect bands to what you observe: conductors versus insulators. In an insulator, the top-filled band is completely full, and the next band is separated by a large gap. With a normal battery, electrons can't easily jump that gap, so they stay put, and current stays tiny. Semiconductors sit in between. Their gap is smaller, so heat or light can promote some electrons into the next band. That creates mobile electrons, and also holes, which act like positive charge carriers. Time to answer the pop quiz. Copper conducts because it has available states in a partially filled band, so electrons can move. Rubber has a large gap, so electrons are stuck in a filled band under normal conditions. To recap, as atoms come together, orbitals overlap and energy levels split. In a solid, Those split levels crowd into bands. Conductors have nearby available states. Insulators have a big gap. And semiconductors have a smaller gap that heat or light can bridge. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.